All right. Well, good morning. Happy Wednesday. And we'll take a look at today's material. So right now we're discussing how to generate values, random values from some kind of distribution. And so, in the context of Monte Carlo methods, a lot of our when we try to estimate an integral like Monte Carlo integration, it relies on our ability to generate random values. And for a lot of these things, there are built-in distributions in R, or built-in functions that generate values from these distributions. And on Monday, we explored inverse CDF, because the CDF basically goes from whatever your support of x is, the CDF turns everything into basically a function that goes from 0 to 1. And then by inverting that, if you can generate a random value between 0 and 1, you can generate values that follow that designated distribution. So, all of these things depend on our ability to generate random uniform values, and I think that's a pretty safe assumption. So we're going to start off by looking at convolutions. So today we're going to look at two methods for generating random values, convolutions and also rejection sampling. So convolutions kind of relies on our ability to generate, this feels really loud, relies on our ability to generate these kind of random values, and then we generate multiple of them and we add them together. Okay, so we either do some kind of transformation or something, some kind of operation, and add them together. So here we say, we have x1, x2 up through xm be some independent random variables, maybe uniform, maybe following some other distribution. And then the convolution is the sum of these random variables. And so a lot of these convolutions that we're going to look at are basically definitions of random variables that you learned. So if you think back to Stats 100B, so a lot of this stuff comes from like 100B, where you learn what is the relationship between, say, an exponential distribution and Poisson distribution, or the relationship between the normal distribution and the t distribution and the chi-squared distribution, all of these kinds of things, and these give way to a lot of the convolutions that we are going to see today. So our one of our most basic ones is the binomial distribution. Okay, binomial is basically you have a Bernoulli. So Bernoulli is a 0 or a 1. Something happens or it doesn't, and the parameter in a Bernoulli is the probability that it happens p. So we're going to just start off with kind of a random uniform value, and then we just say, is that random uniform value less than p? And that will happen with probability p. Okay, and we will generate multiple of these things, so multiple Bernoulli values, and then if we add m of them together, then that will be a binomial distribution, right? So binomial says you're going to repeat the same random Bernoulli trial m times. Each of them have probability p, and then the binomial is, what is the probability of having x successes or k successes, whatever we're looking for. So to generate this on the computer, very simple piece of code here. We can define a function with parameters m and p, and we're going to just create a vector of length m of m random uniform values. I'm going to first start off by setting everything equal to 0. And then for any of the values where u is less than this value p, we're going to change those zeros into ones here. And then I will add up how many ones we have. We sum the x's, and that's going to return a random value here. Okay, and obviously I can condense my code into one line if I just did sum of our unif less than p. That would also do the trick, but this kind of just breaks it out into 4 lines here. Okay, and so one random instance of binomial with m equal to 10 and p equal to 0.6, I happen to get 7. That's just a random one random instance of this. I can try this out, and I can say, hey, let's try generating 10,000 values, right? 10,000 values here, 10 to the 4. And so I'm going to just kind of replicate 10,000 of these things. I'm going to take the function that I wrote, random underscore binomial, and then I'm going to ask R to table this. So it's going to count how many times 0 appears, how many times 1 appears, how many times 2, 3, 4, 5, 6, 7, etc. And we will we'll divide that by 10,000 to see, how many times did the number 6 appear. And so out of 10,000 trials, it appeared 2,474 times, and therefore my empirical probability estimate is 0.2474. And I can compare my empirical values to the theoretic probabilities. So I have the theoretic probabilities using dbinom, and we want to say, okay, 0 through 10, and so on and so forth. And so these are the theoretic probabilities rounded off to 4 decimal places, and I have the empirical probabilities, the kind of what I observed, rounded off to 4 decimal places. And we see for a lot of these things, they are within a handful, maybe plus or minus 1/1000th. So around, give or take, 0.001, right? So I have the theoretic is 0.1996, and here we're getting 0.2007. Here it's 0.2474 is the theoretic, and we got 0.2508. So this one's off by a little bit more than 0.001. Okay. Similarly, we have these. Here for some of the extreme values, we're expecting 1 in 10,000, and we got 3 in 10,000. 0.0016, and what we observed was 0.0012. So it looks like they're pretty close. How do we compare what you got in a categorical? So basically, we have 11 possible outputs. How do we compare what we observed empirically to what we should get theoretically? What kind of test can we run there? So, like if you're rolling a die and you're saying each of these 6 faces should show up with equal probability, and say you rolled the die 1,000 times or something, what kind of test could you run to see if it aligns with the, what do you guys think? Okay, well maybe we've forgotten, but that's okay. Well, we can run a chi-squared test. So here I just created, using base graphics, I just created a bar plot showing the empirical in dark gray and the theoretic in light gray. I guess on the projector it looks black and white. And you can see most of these things are very close. There's a slight difference here and here, small difference there. And the question is, are these differences, are they statistically significant? So one thing we can do is we can do the chi-squared test, right? So the way the chi-squared test, you can do several kinds of chi-squared tests, but here I have a vector of counts, basically, and then we also have a vector of probabilities. So with a chi-squared test, it's important you don't just provide you don't run the vector of probabilities versus the vector of probabilities. The chi-square test is very dependent on the actual sample size, so you need to provide the vector of counts themselves, okay? So here I would take the vector of counts without dividing by n, okay? So we're gonna take, 3, 12, 103, 427. So I'm gonna take the vector of counts, is gonna be my x, whoops, over here, x, why does this keep doing that? The vector of counts for x, and then p will be the vector of probabilities. This p equals theoretical. The theoretical was calculated using d binom over here. So I'm going to compare the counts versus the theoretic probabilities, and I get a p-value of 0.2234. I do get a warning though, okay? Warning in chi-squared test, chi-squared approximation be incorrect. So I don't know what your relationship is with warnings, but sometimes we feel like, oh, if it's a warning and not an error, we're in good shape. Let's just keep going. But a lot of times a warning means you should check out why you're getting the warning. So this is one of those cases where even though the code runs without error, you want to kind of check the warning to make sure that is this going to be working okay. And the reason why we're getting a warning is when you do a chi-squared test, one of the conditions for the chi-squared test is that none of the categories have very, very, very small counts. You want to kind of make sure your expected counts for each of the possible outcomes, each of the possible categories is at least 5. That's kind of our rule of thumb here. And some of these things like 0 and 1, the empirical is the theoretic probability is 1 in 10,000. 1e 0 minus 1e to the negative, so 10 to the negative 4. So we're expecting like 1 in 10,000, and therefore we're not going to get the chi-square test kind of fails here or has problems. So in a situation like this, what we'll do is we will kind of collapse some of the counts. So it's kind of like creating an other category, right? So you could say, hey, what color hair do you have? And the vast majority of people have either black hair, brown hair, blonde hair, red hair, or something like that. But then, some people color their hair and you might have purple hair or blue hair or green hair or something like that. But probably the total number of counts is going to be very small. And so you might just want to have an other category that's going to kind of combine these different colors. Because if you say, in 1,000 people, how many people have green colored hair, you might get a very small number that might not exceed 5, right? Especially if you break out how many people have green hair, how many people have purple hair, how many people have blue hair. The actual counts might be very, very small. And so it might make sense to just kind of combine those, right? And that's basically what we're doing. We're going to take the category, the outputs 0 and 1, and just combine them. So here I'm going to take the counts from 0 and add them to the counts from 1, and then I'm going to delete that. So I'm going to get, take these 3 and add them to 12, and I get 15, and I'm going to delete out the original one. So you have to kind of do this in a manual way. I don't think there's at least in base R, there's not a function that will just kind of combine categories for you. And then we have to do the same thing with the theoretic probabilities. So I'm going to kind of take the theoretic probability for 0 and the theoretic probability for 1, combine those and remove that first one. And then so now I have a vector of counts and a vector of probabilities where I've combined the outputs for 0 and 1. And then I run the chi-square test. I no longer get that warning that the results might be inaccurate. And here I get a p-value of 0.4675. Okay, we also see my degrees of freedom has dropped from 10 to 9, right? So back here, because I had 11 possible values, 0 through 10, degrees of freedom in chi-square test is number of categories minus 1. Here, I've got now only 10 categories, 0 and 1 combined, and then 2 through 10. So I have 9 degrees of freedom, and my p-value is 0.4675, which is greater than 5%, and we would not reject the null hypothesis. And so, although this does not prove that our data comes from the binomial distribution, we can say after generating 10,000 values using our piece of code, we have no reason to believe that the data is coming from a different distribution, coming from a distribution that is not the binomial distribution. So we would say this, this passes our statistical test here. All right, so that is using a random uniform values to get binomial Bernoulli's, and then using a convolution or a sum of them to get a binomial distribution. Okay, let's look at another example, and that is the Poisson distribution. So the Poisson distribution, do we remember? Is it discrete or continuous? Poisson is discrete. It returns a count, and it's used to model like how many times does a random event occur in some span of time. So kind of your classic example is like how many people walk through the door of some kind of shop, right? So you say within a 1 hour span, how many people walk through the door, or how many pieces of mail do you get in a day or something like that? You change it to email or text messages or something. But the assumption there is that everything happens at random times, right? Whereas real life, it's not truly random. Obviously, things are more likely, like if we're talking about customers, you're less likely to get customers at like 6 a.m. as you are at, well, I guess depending on what business you are, maybe say in the middle of the day. Okay, so if you're just like your typical, like some kind of shop, okay, you might have more customers during lunchtime and fewer customers at 6 in the morning or whatever. But yeah, it depends. And so, but you might be able to, like let's say you run a coffee shop where you actually do get a lot of customers at 6 in the morning. You might be able to model this and say, for the 1 hour span from 6 a.m. to 7 a.m., okay, or 6 a.m. to 6:59, we have a certain lambda rate for that hour, and you'll have different lambda rates throughout the day. So 6 a.m. will have one thing, whereas in a coffee shop, maybe 3 p.m. will have a slightly smaller lambda than 6 a.m. I don't know. Okay. 9 p.m. probably smaller still. Well, I don't know. I don't really I have no idea what what it should be, right? But you could say Monday at 6 a.m. versus Tuesday at 6 a.m. versus Wednesday at 6 a.m. or something. And each of these, the outputs of those things could be modeled using a Poisson distribution. So anyway, you have this arrival rate, lambda, which is kind of how the average number of arrivals that we would expect in that time span. And then, but it's random, so some days you get more than that, some days you get less than that. And so how can we model this, okay, is, well, we're going to say X itself comes from Poisson, and then if these are independent, okay, then the sum of these things is also a Poisson, where the lambda rate is also greater. So let's say at 6 a.m. you have this lambda rate of 20, and then at 7 a.m. your lambda is 30, and then at 8 a.m. it's maybe 20 again, okay? And so if you wanted to say, hey, let's just model 6 a.m. plus 7 a.m. plus 8 a.m., and you have these different lambdas, you can just add them up. So 20 plus 30 plus 20 is 70 or something, and you'd say, okay, on my expected count for that 3-hour span is going to be 70 or something like that, okay? So that would be, so that's an example where we have the Poisson. So yes, so the sum of Poisson is also Poisson, and it's just, you just take the lambda rates and you add them together. There is another example, and this is the negative binomial distribution. So you have the geometric distribution, and this is used to model the number of failures before the first success. So it's kind of like, how many times do you have to roll the die before you land on the number 6, right? How many times do I roll the die before I get a number 6? That can be modeled with a geometric distribution, right? So that's exactly what I wrote for this example. What is the probability that we have to roll the die, get 3 non-6s before we get a 6 on the 4th one? And then the negative binomial distribution is used to model the number of failures observed in a sequence of Bernoulli trials before the mth success occurs. So geometric was before we got the first 6, but we can say, what is the probability we must roll, I guess we must roll the die, X times, not just non-6s, but like X number of times before we see the 6 a third time. So it's kind of, it's not like in baseball, you're out on the 3rd strike, okay? And baseball's not really the greatest example because I would say the pitches are not independent. The pitches and the strikes and hits are not truly independent. So it doesn't quite work out, but it's kind of like the idea of like how many pitches do we need to have before we get a 3rd strike or something like that? Kind of, but again, not the greatest because I wouldn't say they're all independent of each other. But you have this situation where you're waiting for the thing to happen the mth time, okay? And you want to say, okay, well, how many of these things do we have to do? So that all we have to do is we just have geometric random variables, and then we add m of those together. So if you're waiting for, how many non-6s do we have to roll before we get the 6 for the 3rd time, I think? Okay, so maybe I have it written correctly. So if you want to have, m successes, you would just take, you would add m of these geometric things together, and you get a negative binomial distribution. Negative binomial distribution with parameters m and p, yeah. So how many non-6s do we get before you get your third 6? Just the sum of geometric ones. So these are just, again, different examples. The chi-squared one I think we're more familiar with. So if you just take a random normal value and then you square it, that will be chi-squared distribution with 1 degree of freedom. And if you want chi-squared distribution with m degrees of freedom, you just take, you add m of these chi-squared distributions with 1 degree of freedom. So you just have, you take your normal random value, you sample m of these things, you square all of them, and that resulting sum, the convolution there, will be chi-squared distribution with m degrees of freedom. All right, I got even more of these examples here. Let me give you your first view quiz answer, which is the letter D. D as in dog. D. D is the first view quiz answer. Okay. So, all of these different probability distributions, I don't know how they picked the names for these things. They are just, it's like they just picked different Greek letters, right? Like we got the chi-squared. Like, why is this chi-squared? Why is this gamma? But anyway, okay, exponential distribution is, so if you have this Poisson point process, which just says things happen at random intervals, the exponential distribution is how much time between one event and the next event. So how much time between one customer and the next customer arriving. And so maybe one customer arrives immediately after the other, and so you have a 0 wait time. Maybe one customer comes in 10 minutes after the other, or something like that. So the exponential can be used to model how much time is in between these things, and it's this. You have this rate parameter lambda, and then the gamma distribution is basically the sum of these exponential things. So how much time before the fifth customer arrives. So let's say you have, like, you're doing tour groups or something, and each tour guide can take 10 people, and you don't set up some kind of a reservation system and people just arrive at random times, and you say, okay, once 10 people arrive, we're going to fill up and we're going to leave, or something like that. It's kind of, I don't know, maybe it's like a ride queue, right? You're waiting for the train to fill up, or the number of seats on that ride to fill up, and then once it's full, then you send it off. So that could be kind of used like with a gamma distribution. So people are arriving at random times, and then once you get to, say, the 10th person, then then it goes. And so you want to say, okay, well, how much time until the 10th person arrives? Well, that's just going to be the sum of 10 independent exponential random variables. So you take, so if you have gamma distribution with shape parameters m and lambda, you take m of these exponential random values and you add them together. Oh, and this is a typo here. It should say gamma distribution. Sorry, this says negative binomial. I think I just copied and pasted the line from the previous slide. Okay, but this is gamma. This should say gamma. Sorry, typo on the bottom of slide 14 there. Gamma distribution. Okay, beta distribution. So we saw the beta distribution at the beginning of our course, where we said, okay, the beta has to be between 0 and 1, and it's a probability. Okay, and so the way this works is you have a bunch of these exponential random variables, because the beta is, what is the probability of a success? Probability of a success, but it's random, right? It's some random number between 0 and 1. And so the way we can do this is we're going to generate a bunch of these exponential random variables with rate parameter 1. We're going to generate, the beta distribution has shape parameters a and b, or alpha and beta, or whatever, but we'll say a and b. And so we add a and b together, and we're going to generate that many independent exponential random variables. So let's say we want a beta distribution with shape parameters 10 and 5. Okay, 10 and 5, which kind of corresponds to, what is the proportion of marbles in here, like blue marbles in here, and I've got some unknown number of marbles here, and I've drawn out a total of 15 marbles. 10 of them were blue and 5 were not blue. Okay, and so to kind of model like what those proportions could be, we're going to generate 15 exponential values, and we're going to take the first 10 and add those up. So we're going to get the sum of the first 10, and then we're going to divide by the sum of all 15. Okay, it's important that these. So see how it says sum from I to A, or 1 to A of xi? These xi's up here are the same xi's, or a subset of the xi's that are down in the denominator. Okay, so here on the denominator we have xi from I equal 1 to a plus b, so maybe we have a total of 15 numbers, the numerator is the sum of a subset, the first 10. If you generate the top 10 independently from the bottom 15, then it's possible that the numerator ends up larger than the sum of the denominator, right? The sum of the numerator ends up larger than the sum of the denominator if you generate these things independently. And that's obviously not going to work for a binomial or for a beta distribution. So it's important that you generate, a total of, a plus b values, and the numerator is the sum of a subset, the first a of those values. Okay. So I wrote that in here. I think in your next homework assignments, I know you guys are working on the Monte Carlo integration homework, but you're gonna have another homework assignment that's where you do convolutions, and I have you generate from a beta distribution, and not almost surely, but I feel like every year in the past, a student, makes it's a very easy mistake to make, but they generate the numerator and the denominator separately, and then they get values greater than 1, and they're trying to figure out why is that, what's going on, and so this is the slide, and I'm trying to point this out, so maybe we'll avoid it. Okay, if you think about what is the numerator, right? This is the sum of a bunch of exponentials. Is a gamma random variable, okay? And then here we've got a gamma random variable. And so here, you can also take two gamma random variables, okay? U, and then the denominator, again, is u plus v. So again, you don't want to just generate one random gamma with u and one random gamma with some other number that's bigger than u, because the numerator could end up being bigger than the denominator. So you're going to generate a gamma u, and that becomes the numerator, and then it's one of the values in the denominator, u plus v. And this, that's where you have that. Okay, and so that will also be a beta distribution. And that just kind of makes sense if you think about, what is the... how are we doing it over here? It's very similar over here, okay? And then finally here we have the t distribution. And so the t distribution, if you recall, it looks like the normal distribution, but it's got wider tails. And the way we make the tails wider is we just basically we start off with a normal random value, z, and then we divide by, the square root of this thing, where v comes from a chi-squared distribution. And so it's a little bit weird. It's a little bit of a weird thing, but this is the t distribution. And I don't know, have I told you about, or do you know about the story of the t distribution? Guinness Brewery, okay, all right. Good little piece of statistics history, right? Okay, so we have the t distribution here. And that's it. So all of these things can kind of be generated. So here the chi-square distribution is a convolution, and then, z by itself is not, but you combine all of these things together as ways for us to kind of generate these things. And so you can kind of take all of these definitions and implement them in code to generate values from any of these distributions. It does feel a tiny bit silly going through all of these definitions here, because there's a function in R called R beta that generates values from the beta distribution. But I also think it's kind of neat to just kind of understand how we could generate these things ourselves. And so for a lot of these classical statistical distributions that we're very familiar with, there are functions that are built in, and we can also use the definitions to generate random values from these distributions. All right, let's take a look at our next topic, which is rejection sampling. So rejection sampling is another method that we can use for generating random values from a distribution. And, inverse CDF is a great method for most of our distributions, and it's going to, if you can get the inverse CDF function, you can just go straight from random uniform, plug it into the inverse CDF function to get your random value. But sometimes finding the inverse of the CDF is hard, or maybe finding the CDF itself is hard, right? So, our go-to example is the normal PDF. We don't have a closed form solution for the CDF of the normal distribution. Now, the computer has a very good approximation, and we end up using inverse CDF using that approximation function. But, you can imagine some other kind of function where we have a hard time integrating, finding the integral of the function or whatever it is. And so finding the CDF is hard. Or maybe you do find the CDF, but then you have to invert it or find the inverse of the function, and that's also really hard. So, how do we do that? Okay, so one thing we can do is we can do rejection sampling. So the goal is to generate random values from this distribution. The PDF of the distribution is F. So that is required. You do need to know at least the functional form of the PDF in order to do rejection sampling. So that's a requirement, is you at least need to know the functional form of the PDF. Maybe you don't know the CDF, but you need to at least know what the PDF is. And here we're going to say, the problem here is we don't know the inverse CDF of this thing. Okay, so the way we're going to do rejection sampling is we need to have a different distribution called G of X. In G of X, we're able to generate values from G of X. And much like importance sampling, so there's actually a lot of parallels between importance sampling and rejection sampling. Although importance sampling is a technique used to estimate an integral, and rejection sampling is used to generate random samples, there are a lot of parallels here. So one thing is that the support of our target distribution F has to be fully contained inside the support of our generating distribution G. So, again, if your target distribution is something like the normal distribution or the T distribution, where you go from negative infinity to positive infinity, you need to have another distribution that goes from negative infinity to positive infinity, okay? Or if it's, just on the positive numbers, it just needs to be fully contained in the support of G. And the other thing is that there is some constant m such that m times G of X is greater than or equal to f of x for all the values in the support of x. So there has to be, I guess, like asymptotically, you cannot have a thing where one distribution decays infinitely faster than the other one. Otherwise, your m might have to be infinity or something, and that's not going to work. But so we're saying there's some finite constant, so that when you take the PDF of G and you multiply it by m, it's going to be greater than the PDF of f for all of these things. Okay, so because of this thing, m times G of X has to be greater than or equal to f of x. The most efficient choice of m is going to be the max of f of x divided by G of x, and nothing larger than that. Okay, anything less than this quantity, the max of f over G, won't satisfy this condition, right? So if you take a number that's smaller than that, right? So let's say f divided by G is 2. And so you would want to keep m equal to 2. If you pick m is equal to, say, 1.5, right? Then there's going to be a spot where f is twice as big as G, and 1.5 times g is not going to be bigger than f. So you need to have whatever f divided by g is, the maximum value there, you need to have that as your constant. Okay, and so the way rejection sampling is going to work is you generate a random value from your generating distribution g of x, and then you're going to calculate this ratio, okay, basically a rejection rate, which is done by f of x divided by m times g of x. And we know that m times g of x is always going to be greater than or equal to f of x because of this requirement, right? So m times g of x is always going to be greater than or equal to f of x. So this rejection rate, or not rejection rate, I guess acceptance rate, okay? Acceptance rate will be at most 1 and possibly something quite less, right? We're going to generate another random value, a random uniform value between 0 and 1. And if this random uniform value is less than this ratio, this acceptance rate, then we'll accept it. And if it's not, then we will reject it, all right? And so with rejection sampling, you end up generating more values than what you accept because you're rejecting some of these values. A little bit like, I think in your homework, you generated values from the normal distribution, and then we said, hey, let's limit it to just values between 0 and 5, I think. And so you end up throwing away some of these things. A little bit like that, okay? Here we're going to generate from g of x, and some of these things we're going to just throw away, okay? So what we're going to do is we're going to try to generate values from the beta distribution, 2, 2, which has this PDF. The PDF is, for beta distribution 2, 2, is, well, you can see 6x times 1 minus x. When you multiply that out, you're going to get a quadratic. And so the PDF for a beta distribution from 2, 2 is basically an upside down parabola that looks like that, okay? And I mean, again, all of these things are a little bit contrived because we could do inverse CDF very easily. We can also, I mean, there's also a built-in function in R, but we will use rejection sampling to just kind of generate this. And so for a candidate distribution, we will use just a random uniform, okay? And so the random uniform going from 0 to 1 also works. And so the random uniform has this PDF. So this is going to be our g of x, which is just equal to 1, and then this is our target f of x, our target PDF, which is 6x times 1 minus x. Okay, and the max value happens at 0.5 here, and so that's going to be 3 times 0.5. This has a max of 1.5. So if you take, what is the max of f of x divided by g of x? We're going to get 1.5, and so that's going to be the m that we use. Okay, so we are going to basically take your g of x, and our m is going to be 1.5. And so if we take g of x and we multiply it by 1.5, then g of x is going to fully enclose our f of x. So I've tried to put that in here. So our f of x is in red, our g of x is in orange, and then we do some calculations here. So I took I I just showed visually here that our at x equals 1.5, our maximum is 1.5, and our most efficient choice is going to be the max of the f of x divided by g of x, which is going to be 1.5, okay? And so finding the max value here, might require a little bit of calculus, and that like you figure out the functional form of f of x divided by g of x. In our case, it's very easy. You take the derivative, set it equal to 0, and solve for the max there. Okay, so anyway, we have m equal to 1.5. And so if I take our g of x, which is just 1, and I multiply it by m, it's going to come up to here. And then what we're going to do is we are going to propose a random value of x between 0 and 1. So sometimes we'll propose a random value like 0.1. Sometimes we'll propose a random value like 0.8 or 0.5, 0.6, 0.43, whatever it is. And some of these things we are going to accept, and some of these things we're going to reject. So I'm going to generate, I guess I'm going to do 100,000. I'm going to propose 100,000 values. And then I'm going to calculate what is the f of the proposed thing. So we're going to look at what is the PDF in our target distribution f, and then we're going to divide by m times g of x. So basically, that's just we're going to divide by 1.5. So if the value I generate here is, if I generate a 0.5, then my acceptance rate is going to be, so f at 0.5, if I generate 0.5 and I divide by g of 0.5, okay? Well, g of 0.5 is always going to be, g is always going to be 1.5, and f at 0.5 is 1.5. So my acceptance rate for 0.5 is going to be 1. So anytime I generate a 0.5, I'm going to accept it 100% of the time. But let's say I generate 0.9. Okay. So my f, so we're going to plug in 0.9 here. My f at 0.9 is going to be 6 times 0.9 times 1 minus 0.9, 0.1. Okay, divided by 1.5. Here I get a 0.54 divided by 1.5, and we're going to get, I don't know what that is, something a little bit more than a third, 1/3. Okay, so something, this is around, I don't know, 0.35-ish or something. Yeah, I'm not satisfied with not knowing what the exact value is. 0.54 divided by 1.5. 0.36. So we will accept it with probability 0.36. So that will calculate my kind of acceptance rate here. I don't know if there's any point in trying to show the chalkboard. So if you plug in x, if you generate a 0.9, then your acceptance rate for 0.9 is going to be 0.36, and then you will generate a random uniform value. And so this random uniform value u is going to be something between 0 and 1. 36% of the time, it will be 0.36 or less, or it'll be less than 0.36. And then the other 64% of the time, it won't. And so this accepted will be true with probability 0.36, and so only a fraction of these things, not we generate 100,000 random uniform values, and some proportion of these things will be true, and then we are going to subset our proposed x values to just those that have been accepted, and so our accepted x is going to be this. So if I do this. This is my histogram of accepted x values. And we can see that the histogram of this thing aligns with our target PDF quite well. So our target PDF is in red. And again, this is a random sample, so it's not perfectly aligned. And so we have a little bit of, just a tiny bit of mismatch right here. But overall, I would say it does a pretty good job of, generating from this distribution. Okay, we could run a Kolmogorov-Smirnov test to see is my empirical cumulative distribution function close enough to the theoretic one. So here is a plot. What do I have here? The theoretic CDF is in red. I don't know why I made the line width so thick. Okay, the theoretic CDF is in red, and then the empirical CDF is in black, and it's really hard to see, but you can see the empirical and the theoretic CDF matches very closely. Here's an illustration of the values that got accepted and rejected. And so here I plotted if U was, say, it was 1, it shows up at the top, and if U was 0, it shows up at the bottom. So the x-axis is the value that was proposed using the uniform distribution. And so we can see, in this diagram, all values between 0 and 1 were proposed equally likely, okay? But then, values where, let's say, values at 0.9, a lot of these values were rejected because, only the height of U here is 0.36, okay? And so, when U was less than 0.36, we accepted it, but when U was greater than 0.36, we rejected it. And so all of the values that were proposed and then rejected show up in red, okay? So this is kind of like throwing just random darts at the wall, and then you're going to just say, I'm going to only accept those that fall underneath this curve. And by doing that, you get, you're going to keep basically values that look like this, okay? And this is just a subset of, say, 300 values, and I did like 100,000 of them. So what proportion did I end up keeping? Well, the proportion that you end up keeping is, theoretically, is going to be 1 divided by m, okay? Because if you think about it, g of x by itself has a total area of 1, and f of x also has a total area of 1, okay? But what we're going to do is we're going to multiply g of x by m, and so the proportion that we end up keeping is going to be 1 over m. And so we can compare how many did we accept. The number of values that I accepted was 66,658 out of 100,000, and that's pretty close to my theoretic acceptance ratio of basically 2/3. All right, let me give you your second view quiz answer. The letter A. A as in apple. A as in apple is our second view quiz answer. All right, let's say we have another distribution, very similar, except we are going to generate, so our target distribution is sine of x. Sine of x, so it looks very similar to an upside down parabola, doesn't it? But our limits are going to be from we'll go from 0 to pi over 2, right? So if you have theta, we start off at 0 and yes. Oh wait, no. Pi over 2 has a max of my brain just stopped over here. Pi over 2 is sine of pi over 2 is 1, right? Okay. Okay, so never mind. We are only doing this first half here. Pi over 2. I'm like, okay, so my brain's glitched out here. Okay, so it's kind of like just the first half there. Okay, so we have to find a value m such that m of g of x is greater than f of x. So, sorry, for a candidate distribution, we're going to go from 0 to pi over 2, okay, which looks like that. And so this is, kind of a similar idea, just looking at kind of the first half of this thing. So here we're going from 0 to pi over 2. Our target distribution is in red, okay? The candidate distribution is going to be uniform, and we will go, we multiply it by this rate, m, which is going to be pi over 2 here. And so now this thing will have the same height of 1 here. Okay, so we will generate values from the uniform distribution, this time from going from 0 to pi over 2, and then we will look at our proposed ratio. So we're going to plug in sine of x, so our f is this function, our g is just, in our case, our m times g is just going to be equal to 1, okay, right, because g is 2 over pi, that is our thing. And so anyway, we have that. And we will look at which values that we accept. And we do this, and indeed we get values that look like the distribution that we want, okay? Our accepted values versus our the PDF here, okay? And then and here again you can do empirical CDF versus the theoretic CDF. So here our theoretic CDF, if you integrate, will be 1 minus cosine, and so it looks like that. We're going to plot our empirical CDF, and indeed they match up very closely. And here's a plot of what values we proposed. So uniformly, the values are proposed uniform across 0 to pi over 2, and then values close to pi over 2, all of them are accepted. Values close to 0, all of them are rejected, and then in between you get some rejected, some accepted. And we can see values that show up that are less than our acceptance ratio get accepted, and those that are above it, when the uniform value is above it, it gets rejected there. Okay, we will we'll visit this example again next week. Folded normal, I've got some animation to go with it, but here's an example where we have our PDF is the folded normal, and for our candidate distribution, we have the exponential distribution. So remember, the folded normal, we're taking our normal distribution, and then we're going to draw a line at 0, and basically, we're going to just take the absolute value. So our folded normal distribution ends up looking like this. This is going to be our f of x, and then we're going to propose from g of x, okay, and our g of x will be the exponential distribution, okay. And so our g of x looks kind of like this, okay? If you think about the decay rates here, it's going to be okay because our g of x decays at a slower rate than our normal distribution. So our normal distribution decays at a rate of negative x squared over 2, and then this just decays at a rate of e to the negative x. And both have a support of basically all positive values, so we're okay here. So this is our folded normal is in red, and our exponential is in orange here. And so what we need to do is we need to multiply the orange by some constant so that it is taller than the red distribution everywhere, okay? we could not, like, let's say if your target distribution was exponential, and you say you were going to propose, if things were reversed, where you wanted your target distribution was the exponential, and then your proposal distribution was the folded normal, there would be no constant, because as you go out towards infinity, the exponential is going to be, this folded normal is going to get decays much faster, approaches the asymptote of zero much faster than the exponential distribution, and so like the m has to be like an infinity towards the end for the whole thing. But in this direction, it's going to be okay. So here we're going to take f of x divided by g of x. So this is a little bit of a pain, but it's not too bad. Okay, so here we have the PDF of our target distribution, which is here, our folded normal. The PDF of our proposal distribution is here, and we can do this. And so just using a little bit of kind of thinking here, we can say the maximum of this without having to actually take the derivative of this directly. We can just say, okay, we got e to the negative of this, and so the maximum of this quantity is going to happen at the minimum of x squared over 2 minus x, okay? And then this is going to happen when x equals 1, and so if I plug that in to here, we are going to get this quantity, e to the 1/2 times 2 over root 2 pi, and that's going to be around 1.32. So we're going to take we're going to multiply g of x times 1.32 to get the distribution that we want, okay? And so when you do that, if you take the orange and you multiply it by 1.32, we can see the resulting distribution in blue perfectly encloses the red distribution, all right? And it just kind of touches right here at x equal to 1. So it's so blue is taller than red everywhere, which is great. Okay, and then I guess another. So here's a situation. So I just started and I just say, here, we're going to use the exponential distribution. But we would not be able to use something like the uniform distribution, because the uniform distribution, if you say, what is the support to the uniform distribution, you cannot have it be unbounded, right? Like you can't just let x say, I'm going to generate a random uniform value between 0 and positive infinity. We can't do that. So the uniform distribution is bounded on the maximum side. And even if you chose like some ridiculous number, like 1 in like uniform from 0 to 1,000, okay? And obviously like the folded normal distribution rarely generates anything over, say, 6, okay? So you might be able to get away with just saying, hey, let's go from 0 to even 10 or something like that, okay? And but then then your g of x is going to be 1/10, and then you'd have to scale it up by a very large m. Okay, so anyway, here we're going to just generate values. We propose values from the exponential distribution, and our target distribution is just the normal PDF times 2, right? So I've got our target is 2 times the normal PDF. My proposal distribution, my proposal PDF is just the exponential distribution. And then I have this constant m, which is approximately 1.32. I think I just plugged that in there, okay? And then we're gonna, so that gives me my acceptance ratio. I'm gonna generate a bunch of uniform values between 0 and 1. We're gonna see how often are those uniform values less than r of x, and then we will accept them, okay, if it is. And so looking at this, indeed, this looks like our target distribution. This is what we want, okay? And here's our comparison between the theoretic CDF and our empirical CDF. And here is a picture showing what values we have, okay? And so what we can see is that, the density of dots proposed here looks like there's a uniform density, which means values closer to zero are proposed at a much higher rate than values, say, between 4 and 5, right? So we can see that how often were values between 4 and 5 proposed? They were proposed very rarely, which makes sense because we are using our exponential distribution to propose values in the first place. And then after we propose values using the exponential distribution, we only accept those that fall underneath the target PDF, in our case, the normal PDF times 2. And so we can see the exponential distribution kind of proposes values near 0 a little too frequently compared to the normal PDF. And so here, some of those values near 0 get rejected. The exponential distribution at 1, anytime it proposes a value near 1, those will get accepted with 100% probability. And then with the folded normal, we rarely accept values above 3. And so you can see the exponential distribution actually, proposes values above 3, not super frequently, but, certainly more frequently than the normal distribution. And so anytime it, proposed a value greater than 3, almost all of those values, I think, got rejected in our sample here. So looking at our sample of 300 values, all of these, anytime the values were proposed greater than 3, those were all rejected. But again, because we're using the exponential, there's only a few values above 3 were even proposed in the first place, because the exponential, says, don't propose very many values out here. Versus, say, if we used a uniform distribution. So even if let's say we used a uniform distribution from 0 to 5, okay? So 0 to 5, we would miss out on part of our normal distribution because technically the normal distribution could generate values greater than 5, but we can just say, hey, let's approximate this. And you can imagine if you just kind of have a flat line going over here, you would be rejecting a very large proportion of values. And so the exponential here will be a little bit more efficient as far as a rejection sampler. Okay, and again, there are a lot of similarities between rejection sampling and importance sampling. And I don't like the name importance sampling to begin with because it sounds like it's a sampling algorithm. But the importance sampling is actually used for estimating the value of the integral, and we weight our values. So importance sampling, we take all of our values that were generated from, say, g of x, but we just weight them. So we accept everything, but we weight them a little bit differently. And with rejection sampling, we use rejection sampling to get a random sample from our target distribution, and we do throw away quite a number of our proposed values here. Okay, let me give you your final view quiz answer for today, and then we'll end our lecture. Our final view quiz answer is the letter B, B as in bear, and that's it. We'll go ahead and end here, and we will see you next week. Next week's already 4th week. Man, okay. Things are going quickly. All right, we'll see you.